Good morning, Calculus BC. Today, although I'm not here, we are still going to push forward. We are going to talk about Section 9, the representation of power series. Okay, this is pre-recorded, so if at any time you need the sub to pause it because I'm going too fast, go ahead and do so. I'm teaching to an empty classroom right now, so that is a possibility. I am going to post this online, so if you need to go back and watch it this weekend, it will be there for you. Okay? All right, so I would like you to think about this function right here. F of x is 1 over 1 minus x. Okay? Does that look familiar if we think back to some of our series from when we very first started this chapter? What I'm hoping maybe some of us recognize is we have this rule, A divided by 1 minus R. And that is a rule for when we add up which kind of series? A geometric series where the absolute value of R is less than 1. Okay, so let's go back to this function up here. Do you agree that this follows the same pattern as A over 1 minus R? What we can do here is with our function 1 over 1 minus x, we can compare it to that A divided by 1 minus R, and we can say, well, A is 1, and R would be x, so that 1 over 1 minus x would be the sum from n equals 0 to infinity of 1, which is A, times R to the n. Okay. Which, this is the sum, 1 plus x squared plus x cubed, etc. Now, a couple things we need to point out. First of all, where is this series centered at? Since it is only x to the n, we are going to say that this is centered at x equals 0. We also care about an interval of convergence. Okay? Now, what makes this nice is we used a geometric series to represent this function, and we know that geometric series only converge when the absolute value of R is less than 1. So since that's the case, and our R is x, we know that the absolute value of x is less than 1, which means our interval of convergence would be -1 to 1. X can be smaller than 1, but bigger than -1. Okay? And this is basically the trick that we are going to use for this section. Okay? We are going to take our functions and we're going to basically trick them into being the sum of a geometric series so we can write our function as a series. Okay. So we're going to stick with our same function, 1 over 1 minus x. Okay. But now I want to go ahead and center this somewhere else. we want to center it at x equals -3. Okay, now I can't just change the value of an expression, okay, or of a function. Okay, so we're going to have to be a little careful here. All right, now if we want this to be centered at 3, then we need this to be we're centering at x equals -3, which means we need this to be x plus 3. Okay, we need to account for that shift to the left. Okay, well, our denominator still needs to be 1 minus x. That still needs to be a minus because it has to be subtracting the x. Now, what number needs to go right here if we still want that denominator to be 1 minus x? I'm hoping you're turning to your neighbor and saying 4, because 4 minus a positive 3 is 1. So we have not changed this fraction. We have just adjusted the way that it looks. Okay, they are still mathematically equal. Okay, now in order to write this as a geometric series, we need this to be a divided by 1 minus r. Okay, well, in the spot where we need a 1, we actually have a 4. So what we need to do is we need to multiply numerator and denominator by 1/4 so that we can have a 1 for our geometric sum. Okay, so what we're going to have is 1/4 divided by 1 minus x plus 3 over 4. Okay, now this is in the form of a over 1 minus r. So let's go ahead and write this as our power series. So we have the sum from n equals 0 to infinity of a times r to the n power. Okay. I am perfectly fine with you leaving it like this, but I want you to notice that we have a 4 right here, and technically we have a 4 to the n right here. So you are going to see those grouped together as 4 to the n plus 1 in the denominator, and then x plus 3 to the n in the numerator. Okay, so if you can see that, you can go ahead and consolidate it to just, one numerator, one denominator. It's one fraction, I guess is what I'm trying to say. Okay, so what about this interval of convergence? Okay, we know that our r value right here is x plus 3 over 4. And we know for this to be able to converge, the absolute value of x plus 3 over 4 needs to be less than 1. Okay, well, the absolute value of 4 is 4. Okay, so I'm going to go ahead and write it like that, which means the absolute value of x plus 3 needs to be less than 4. Okay, so what we have, you can look at this one of two ways. You can either solve this inequality, or we are centered at -3, and our radius of convergence is 4. Okay, so if we're centered at -3, then our interval of convergence would go from -7 to +1. Okay, now, like I said, all of today we're basically rearranging our function until we can write it as a geometric series. So I'm just going to do a bunch of different types of examples so you can see how that can happen. All right, so I did a very straightforward example here. This one, we took that straightforward example and we centered it somewhere else. Let's go ahead and do something a little bit different. Now, I'm going to give you 1 over 1 plus x cubed. And I want to write this as a power series. Okay. The whole trick is to finding a way to write this as 1 over 1 minus r. So, are we able to do that? We can write this as 1 minus 1 minus negative x cubed. And here I would argue that this is in the form of I was saying 1 over 1 minus r. We really need a over 1 minus r. Our numerator is 1, and so that is fine for now, but really the numerator can be anything. What we're focused on, well, any constant, okay? We need a constant a over 1 minus r. Sorry about that. So what we're going to do is we're going to call r negative x cubed, and we know our a value is our numerator, 1. So our series representation for g would be a, which is 1, times r to the n power. Okay? Now, this is probably not how we would see a series written, okay? First of all, I see that we have a negative raised to the n power, and we really like our alternating pieces to be separate from the rest, okay? And then we can write x to the 3n after it, okay? This is probably how you're going to see it rearranged. Okay? Now, since x is all by itself, there's nothing like added or subtracted with the x, we know that this is centered at 0. Our r is x cubed, and we know that the absolute value of r needs to be less than 1. Okay, x cubed less than 1, it's going to be an interval of negative 1 to 1, since we're centered at 0. Okay. Now, I would like to take this function and write it as a power series centered at negative 2. Okay, so we're going to have to do a couple things to this series. The first thing is that we need this to be centered at negative 2, which means when we subtract x, we really want to subtract x plus 2, so that we are centered at negative 2. Now, we can't change the value of our fraction, so we need to figure out a way for our denominator to still be 5 minus x. Okay, so we're going to go ahead and write a 7 here, because 7 minus a positive 2 is still going to give us that 5 right there. So it is still 5 minus x, it's just written differently. Okay, now, our ultimate goal is a over 1 minus r. So that 7 is now what we want. So we're going to go ahead and multiply numerator and denominator by 1/7. That way we have, that way we have 4/7 divided by 1 minus x plus 2 over 7. So our function, h of x, which is 4 over 5 minus x, is the series from n is 0 to infinity of a, which is 4/7, times r, x plus 2 over 7, to the nth power. And like before, we can go ahead and rewrite this. Okay, we can combine our denominators to be 7 to the n plus 1, which means we would have 4 times x plus 2 to the n power in our numerator. Now, since our r value was x plus 2 over 7, we know that has to be, the absolute value of that has to be less than 1. Essentially, we have the absolute value of x plus 2 is less than 7. You can do one of two things. You can solve that inequality, or you can think of this centered at -2 with a radius of 7. So -2 plus 7 would be 5, and -2 minus 7 would be -9. Okay. I'm going to go ahead and give you some operations that we can do with power series. Okay, these are just some properties. Okay, if we have f of x, which we write as the sum of a sub n times x sub n, and g, which we write as the sum b sub n x sub n, then one operation we can do is f of k times x is the sum of a sub n kx to the n. Okay, we kind of saw that on Monday with our Taylor polynomial, that cosine of x versus cosine of 2x. All right. The second one is if we have f of x to a power, then in our series we can write x to the n to the power. Well, yeah, those would be multiplied, so just write it like that. We can raise that to a power. And then third, if f and g are being added or subtracted, then we can combine the power series together. Okay. Couple wacky examples for you here. You guys like curveballs, right? Okay. Now here we really we have that x thrown in the numerator. Okay. So that's kind of throwing us off of our game here. So I'm going to give you a way to break this up. Okay? Now, since our denominators can be written as x plus 1 and x can go ahead and break this up into the sum of two power series. Okay. Okay. If you were to go ahead and solve that by partial fraction decomposition, I'm going to go ahead and save you some time if that's okay. We have 1/2 times 1/2 divided by 1 plus x. And then I'm going to go ahead and rewrite this as 1 minus x, which means that's going to be a negative. Both a and b both end up being 1/2. Okay, so this is one way we can do this. Now, essentially, okay, this 1 plus x we can rewrite as 1 minus negative x. Okay, so we have the sum from n equals 0 to infinity of a times x times r to the n, excuse me, plus the sum of a times r to the n. So what we can do is we can take that 1/2 out, and we have an alternating series here for our first one, negative 1 to the n, x to the n. And then we can subtract 1/2 series from 0 to infinity of x to the n. Okay. Now, we can go ahead and factor out that 1/2. Also, we can go ahead and factor out the x to the n, leaving us with negative 1 to the n minus 1 to be multiplied to the x to the n. So here's where that negative 1 to the n is coming, and then here we only have x to the n, so when we factor it out, we're left with 1. Okay. Now, just for kicks, let's go ahead and look at this sum. Okay? If we plug in 0, we get 0. If we plug in 1, we get negative 1 minus 1 times x to the first. If we plug in 2, we have 1 minus 1, which is 0. If we plug in 3, we get negative 2 here, x cubed. If we plug in 4, we get 1 minus 1, x to the 4th. Okay. If we plug in 5, we get negative 2, x to the 5th. I hope that you are seeing a pattern. Okay? Because what we can do, since we see this pattern, is we can go ahead and write this as the sum from 0 to infinity. I see that we have negative 2, and we're only getting every odd x to the power. So we can write our power as 2n plus 1. That's how we express an odd number, 2n plus 1. Now, we have 1/2 times negative 2, so we can go ahead and express this as negative the series of x to the 2n plus 1.
How can I help you this afternoon?
Okay. Now, I know that's a very crazy example. I don't think you have one like this in your homework. Actually, don't quote me on that one. I can't remember. It is possible that we have one on Tuesday like that. But I just wanted to show you what that would be like. Okay. Now, I have 3 more examples and then we're going to be done. All right. Here we have a function 2x squared over 1 plus x cubed. Okay. Now, in our last example, we went ahead and we did partial fraction decomposition. Now, it is possible to do this last example like we're going to do this one right here. If you want to play around with it, you sure can. All right. What we're going to do is we're going to go ahead and write this as 2x squared times 1 over 1 plus x cubed. And since we want this to be written as a geometric series, we're going to go ahead and, like we did earlier, write this as minus negative x cubed. Okay, so this is using that property, nope, not that property, just kidding, don't quote me on that. Okay, I got ahead of myself. Here we go. So what we can do is we can take 2x squared and multiply it to the series from n equals 0 to infinity of a, which is 1, times r to the n power. Okay. So we have 2x squared. Now we can do this because this series is in terms of n, so it's okay to be multiplying by that x. All right. So we have 2x squared series from n is 0 to infinity of negative 1 to the n, x to the 3n. All right. And you might remember our rule that when we are multiplying with the same base, we can add our exponents. So what we can do is we can go ahead and bring this 2 inside. We have negative 1 to the n, and then we can combine these two x's to be x to the 3n plus 2, and here is our series. As long as you can write it as a number, a, over 1 minus r, we can write a power series. It's just a matter of seeing what trick we need to use in order to do that. All right, 2 more. Here we have 1 over 1 minus x squared, okay? We cannot take this and write it as a geometric sum. We do not have a over 1 minus r, and that denominator cannot be written as 1 minus r because it's really 1 minus 2x plus x squared. That's not going to be a possibility. However, we know that 1 over 1 minus x squared is the derivative of 1 over 1 minus x, which we know is, I'm going to move this over, otherwise I'm going to be too squishy. Okay, we know this. So we know that 1 divided by 1 minus x is the series from n equals 0 to infinity.
How can I help you?
Of a times r to the n power. Okay? Now, here's where it gets exciting. We get to take the derivative of a series. First of all, when we take the derivative of a series, we're going to have to be careful here. So I want to start inside. The derivative with respect to x of x to the n power is nx to the n minus 1. And since we have to use the power rule, our power decreased by 1, which means we can't start at 0, we have to start at 1. Our interval of convergence, okay, R is still X, centered at 0, our radius is still, or our interval, excuse me, is still negative 1 to 1. All right, that was that example. What do you think the next example is going to entail? I know you're really excited. Okay, I want to write this as a power series. Now, obviously, does not look like A over 1 minus R. So we need to find a relationship. We know that the antiderivative of 1 over 5 minus x is negative the natural log of 5 minus x, which means if we're trying to represent the natural log of 5 minus x, then we need negative the antiderivative of 1 over 5 minus x dx. Which means we're going to have to take negative the antiderivative of the power series in the 0 to infinity of a, oh, what do we got to do? Can't do that yet. We need to change this to 1/5 over 1 minus x over 5 dx so that we have a over 1 minus r. And then we can go ahead and write the series from 0 to infinity of a times x, excuse me, r to the n power. All right, I'm going to go ahead and rewrite this as x to the n over 5 to the n plus 1. Go ahead and consolidate that. Now, if we find the antiderivative, right, first of all, we still have that negative out front. We have n equals 0 to infinity. Power rule. We are taking the derivative with respect to x. So we increase the power by 1, divide by that power, and we still have that 5 to the n plus 1 because it's not, there's no x, so we treat it as a constant. Of course, we have that plus c. If you plug in x equals 0 to both sides of that, we get the natural log of 5. So what we have for our answer is negative the series from 0 to infinity of x to the n plus 1 over n plus 1 times 5 to the n plus 1 plus the natural log of 5. Right, so there's your power series. So, please attempt all problems on your homework. Okay, you have, let's see, 5 through 15 odd, number 17, and 19 through 21. 19, 20, and 21 are the ones that will deal with derivatives and antiderivatives, All of the rest will be ones where you just have to tweak the fraction. Okay? So do what you can. We will reevaluate on Monday, but everyone needs to attempt each problem, Tuesday. Everyone needs to attempt each problem by Tuesday so that we can have a productive class period. Okay? The rest of the time is yours. We will see you on Tuesday.